In this video, we're going to discuss the concept of Ka and pKa for acids. First of all, of course, we know that when we put a weak acid into water, it will dissociate partially. So it does not dissociate 100%. Here we have acetic acid. When put in water, it will dissociate and will produce the hydronium ion and the conjugate base, the acetate ion. At equilibrium now, again, this dissociation will eventually reach equilibrium. At equilibrium, our concentrations of our weak acid, our concentrations of hydronium, and our concentrations of the conjugate base, the acetate, at equilibrium, all of those will be constant. So there will be no change in those concentrations. So since this dissociation reaches an equilibrium, we can write an equilibrium expression showing that. Now, just a bit of a review. Of course, when we write an equilibrium expression, let's look at this theoretical or hypothetical reaction here. A plus B is in equilibrium with C plus D. The equilibrium expression is essentially the concentration of our products raised to whatever molar coefficient we have here, raised to that exponent, divided by the concentration of our reactants. Now, anything that is a pure liquid or pure solid, so if this was a pure solid or this was a pure liquid, we would not include that in an equilibrium equation, equilibrium constant expression, because those concentrations of pure solids and pure liquids remain constant. So only gases or aqueous solutions do we include in an equilibrium constant expression. And an equilibrium constant expression gives us a lot of information about a reaction. It gives us information about how far it proceeds to the right or to the left. It gives us information about the concentrations. It allows us to calculate equilibrium concentrations for a particular reaction. So we could do the same thing for acids and bases. When we have an acid dissociation, an acid dissociating in water, and it reaches equilibrium, we can write an equilibrium constant expression. However, instead of Kc, because it's an acid, we call that Ka. So if we wrote a dissociation equilibrium expression for the dissociation of acetic acid in water, it would look like this. It would be our product, hydronium, times the concentration of hydronium times the concentration of acetate, divided by the concentration of undissociated acetic acid. And again, water is a pure liquid. We would not include that in here. And if you think about this, and again, understand what this will tell you, the more dissociation, the more the acetic acid dissociates, the higher the concentrations of hydronium and acetate. So an acid that dissociates a lot will have a high concentration of the products and a low concentration of the undissociated acid. So mathematically, if we plug those concentrations in, Kw would tend to be very large. That's why strong acids, we don't talk about Ka values for strong acids. Since they dissociate completely, our Ka value would be too large to measure typically. So the Ka constant is a measure of the extent of dissociation of a particular weak acid or a molecule that has an acidic functional group. So the larger the Ka constant, the stronger the acid, the more it dissociates. And as I mentioned before, strong acids dissociate 100%, so their Ka values are too large to calculate. So Ka values only apply to weak acids. The Ka constant is sometimes expressed as a pKa. Much like the hydronium ion concentration can be expressed as pH, the hydroxide concentration can be expressed as pOH, the Ka value can be expressed as pKa, and a pKa is the negative log of our Ka value. Just like pH and hydronium are inversely related, the Ka value and pKa value for an acid are also inversely related. In other words, if you have an acid that has a large Ka, that corresponds to a small pKa. And of course, a small Ka, which would indicate a weak acid, results in a large pKa. So weak acids that are relatively strong have large large Kas and small pKas. Weak acids that are relatively weak have smaller Kas and larger pKas. So again, you don't necessarily have to just memorize these sentences. Don't try to memorize those sentences. Understand um, how Ka is a measure of the dissociation of an acid and how you calculate that mathematically. Then you can, when you understand that, then you will understand um, these sentences and not necessarily just have to memorize them. Let's try a problem here. Write a Ka expression for the dissociation of carbonic acid in water. If the Ka value for this acid is 4.3 times 10 to the minus 7, calculate its pKa. So you're asked to do two things here. Write your equilibrium expression, the Ka expression for the dissociation of carbonic acid in water. Now you're given the Ka and you're asked to convert that to a pKa. So pause the video and give that a try. Okay. So the first thing we would want to do is write our Ka expression. To do that, we'd probably want to write a balanced chemical equation first. Our carbonic acid plus water gives us HCO3 minus bicarbonate plus hydronium. So this will deprotonate, and water, so this will be my weak acid. Water will be my weak base. Water will accept the proton, forming bicarbonate and water and hydronium. Now, carbonic acid, it can lose another proton, but it will only lose one at a time. So here we're writing a Ka expression for the first dissociation of carbonic acid. The Ka expression will be products over reactants. So that would be the concentration of hydronium times the concentration of the conjugate base, the bicarbonate, divided by the concentration of undissociated carbonic acid. Of course, we leave the water out because it's a pure liquid. Its concentration remains constant. Second, you're asked to calculate the pKa. Well, we have our Ka value, and if we take the negative log of that, we get 6.37. So the Ka value is 4.3 times 10 to the minus 7. The pKa is 6.37. So practice some more of these problems. Again, get comfortable writing Ka expressions, calculating Kas and pKas, and most of all, be sure to understand what these values tell you about a particular acid.